In number 41, there's a lot going on right here. They've given us a cubic function, x cubed minus 2x squared plus x, and they're asking us to find 4 different things here, although it's really 2 different things, and a couple of them kind of get lumped together. You'll see why in a second. So this is what they are looking for here, guys. All right, so they want us to find intervals of concavity, points of inflection, all critical points, and then any local max or min values. It is important to say local max or min, because with a cubic function, everybody, that has an unlimited domain, we know already that this graph is going to go down on the left and maybe do a little dip in the middle and then go up on the right. A cubic function such as this has no absolute max or absolute min. What we're probably looking for is a local max that's right here and a local minimum that's right there a little bit further to the right. But I don't want to assume. Let's dive in. Now, I thought it was funny that they asked you for these 4 things in this order. I probably would have asked you for these 2 things first. Why? Because both critical points and a local max or min come from the first derivative. So we're going to find f prime of x, which of course you have to do before working on these things, which come from the second derivative. So here goes, guys. F prime is going to give us a 3x squared and a minus 4x plus 1, and we would want to know, where is that first derivative equal to 0 or undefined? Well, it's never going to be undefined. It's a polynomial function, but I think there's a good chance this equals 0 somewhere, and hopefully this thing is going to factor. Let's see what we've got. Signs would be the same and both negative, and if I went 1, 1, that's a minus 1x, that's a minus 3x. There's the minus 4x that I needed. So, all right, go us, everybody. We got that here. Okay, so if we set each factor equal to 0, here we would get an x equals positive 1/3, and here we would get an x equals 1. Certainly, those are both in the domain of this function, so those are our 2 critical points. In fact, I'll go ahead and label that right here. The critical points are x is equal to 1/3, and x is equal to 1. Remember, guys, the definition of a critical point is just a spot where your first derivative is 0 or undefined. So even though I don't know yet if anything interesting happens at these points, meaning if they give us a local max or a local min, they're still critical points, regardless of what happens next. Okay, time to choose some test values, everybody. I'm going to switch to purple right here. Less than 1/3, I'm going to go with x equals 0. In between the two, that's not a whole lot of fun. It actually might be easier, would it? I'll just go with x equals 1/2. Don't overthink it. And then bigger than 1, I'm going to go with x equals 2. We are trying to find out information about the behavior of this function, and it's the first derivative that tells us that. So we're going to f prime of 0, and the best place to go here is the factored form of that derivative, because we can just play a sign game. If x is 0, 3 times 0 minus 1 is negative. 0 minus 1 is negative as well. Negative times negative is positive. So our function is increasing for all x values less than 1/3. Now we're going to try 1/2. F prime of 1/2, and here we go. 3 times 1/2 is 1.5 minus 1. That's positive. But 1/2 minus 1 is negative. Positive times negative is negative. F is decreasing on this interval from 1/3 to 1. And let's not make an assumption, even though if you remember a minute ago, I think we knew what this third degree function looked like. Let's not assume that this thing increases, though. If we plug in 2, f prime of 2, 3 times 2 is 6 minus 1 is positive 5. So that factor is positive. This factor is positive as well. Positive times positive is positive, so f increases on this interval here. So they wanted us to find critical points, which we've done already right here. The next thing they asked for was to find if we have any local maximum or minimum values. Well, we do here. At x equals 1/3, that's a critical point, and at that spot, our first derivative changes sign from positive to negative, which means the behavior of our function changes from increasing to decreasing. That, everybody, is the definition of a max. So we have a local maximum here at x equals 1/3. And then at x equals 1, right over here, our first derivative changed sign from negative to positive, which means our behavior changed from decreasing to increasing. That is the definition, or the test really, for a local minimum that occurs here at x equals 1. So right there in red, that is the answer to what I guess is that fourth question, whereas right here was the answer to the third. Okay, guys, that is as much information as we're going to squeeze out of the first derivative here. That's everything we would possibly want to know about it from there. Now it's time to move on to the second derivative, which is going to give us the answer to the first two questions here about intervals of concavity and points of inflection. So we got to find f double prime of x. Let's see how this one works out. Differentiating f prime right here, that's going to get us, okay, not great, a 6x minus 4. Again, it will never be undefined. This is just a simple polynomial, but it will equal 0, where, guys, bring that 4 over, divide it by 6 at x equals 2/3 when we simplify that. I'm going to box that up now, and should have done this earlier, sorry. All right, let's zoom in where we need to now. Let's see what's going on at x equals 2/3. What we have right here is a spot where our second derivative is equal to 0. Right now, this is a potential point of inflection, but we probably shouldn't assume, although I have a feeling this is going to work out just fine. All right, let's pick an x value less than 2/3. How about 0? Greater than 2/3? How about 1? And if I'm trying to learn something about concavity, I go to the second derivative now. So I want f double prime of 0. And what does that do for us? 6 times 0 is 0, minus 4 is negative. We are concave down for all x values less than 2/3. And again, let's not assume. Let's go f double prime and let's put in 1 now. 6 times 1 is 6, minus 4 is a positive 2. We are concave up. So they were asking us to find intervals of concavity. That was really the first question. So we now know that this graph is concave. The order in which you answer this doesn't matter, guys. It's concave down, if I read it from left to right, for all x values that are less than 2/3, or as an interval that would have been from negative infinity to 2/3. It is concave up for all x values that are greater than 2/3. Or you could have set an interval from 2/3 to infinity. And then, guys, because our second derivative changed sign from negative to positive right here, we can say that we have a point of inflection at x is equal to 2/3. And there, if I box all of that up, those are the answers to the first two questions that they asked us. So, like I said, I think it was a little weird the order they asked you those two questions in, but I think we've given them everything that they need here for problem number 41.